on computing. So please remember, these slides are a little bit wordy because they kind of serve as our textbook for the course. Really what I'm going to try to do as we go through them is just summarize the key points, but do feel free to look through them in detail on your own time. So when we define computing, we're just going to define it as the operation of actually doing math or doing computation. So what you see on this slide is that the idea of automating it through hardware is a relatively old ideal. We have the reference to 2700 BC back to the abacus, but really what we're going to focus on is digital computing machines. And until 10 years ago, we could just call digital computing machines any type of modern computer. But if you're familiar with what's going on with revolutions in quantum computing, it may turn out that the computers of 20 to 30 years from now that really revolutionize a lot of the fundamental problems that we're attempting to solve in computation, which are largely related to applications of artificial intelligence, may be enabled through a paradigm of quantum computing that's actually analog in nature. So if a lot of that didn't make sense, it's okay. Just know that the way that computers work now, from a digital perspective, which we'll define more formally here in a minute, may not be the way that at least modern supercomputers work 20 to 30 years from now if the analog paradigm of quantum computing turns out to win out. Ignoring all that, what do we mean by a digital computer? Well, I want you to think of a digital computer as having two attributes. First and foremost, understand that the way that it stores information is in a discrete form. Particularly, it is in what we would call a binary form. And we'll talk about what that means in a minute. But before we talk about discrete representation of information, we have to realize that the world around us is analog. The audio that you're actually listening to now, when it's actually generated out of my mouth, it turns out that when it's actually captured by the digital camera and stored on the computer, eventually stored on YouTube and coming out on your sound card, for a portion in the middle, it's actually represented in digital form or discrete form. However, at the beginning and at the end, it's an analog form. And what an analog signal is something that is continuous in time, meaning it's technically defined at any point in time. And it also can take on it at all of those points in time, any continuous amplitude value. So if you think about sketching it out, it's just going to look like a standard function that you would draw in a math class. And when you draw it graphically, it feels like you can represent it using a little bit of information. However, think if you were to try to store all of those values that are stored in a graph, maybe even something as simple as a line. If you were to write out all the ordered pairs that are on that line, how many ordered pairs are there? Well, remember that on a line, the domain is all real numbers. That means the allowable x values. And depending on your slope, in general, the range of a linear function is also all real numbers for everything other than a horizontal line. So if you had to write all real numbers out, you can't do it. You can't store that in finite form. So in order to be able to store anything in meaningful hardware, it has to be represented in a discrete form. So particularly our modern digital computers store information or numbers, everything can be broken into numbers, in what is known as the binary number system. Now, what is the binary number system? Well, maybe it's a little bit easier to think about the way that we write numbers now. So maybe you think about a number like 949 or 10,572. And I'm talking about whole numbers for now, just to keep it easy. But hopefully you realize that when you make those numbers, you have to make two decisions. First and foremost, for each place value that you write a number, you have to choose a digit. And those digits are between 0 and 9, so 10 total digits. And in addition, when you arrange the digits, kind of the meaning or the value of the number is interpreted by taking each of those digits and weighting them by their place values. So that's going all the way back to whenever you learned what numbers meant originally. But the reason I bring that up is the same ideal applies to binary. And we're going to describe this in detail on the next slide. So if it's not clicking now, just give it a little bit of a minute. But a binary number is just a way to represent information using a number system, which has only two digits, 0 and 1. And each place value is going to be represented as a power of 2 rather than a power of 10. So in addition to that very simplistic, easy way of storing information in ones and zeros, digital computers, believe it or not, only know how to do a simple amount of things. And that might be like incredibly complicated to you, given the fact that you're watching this on a computer on the internet and you're like, well, how under the hood, what that computer actually is, the processor, how can it only do a very simple set of instructions? And that's exactly what it's called. It's instruction set architecture. And the reason is those simple set of instructions can be combined into more complicated programs. And that's what it actually means to program a computer that really can do anything. So you can think about it. I always give the analogy, if you're training a baby from scratch and all that it can do is crawl and it can reach and so on, you're tempted to say it can't do anything. However, if you give it complicated instructions, if you tell it particularly how to crawl and particularly how to pick things and so on, you might find that by programming its basic instructions, it's able to do more than you would originally think on the surface. And that's exactly how modern computers work. It just happens that they can do those simple things really, really quick. And the simple things they can do can be programmed to represent any complex task that you would want it to do. So what is a computer? Is it just whatever you're watching this on now? Maybe it's your phone, maybe it's your laptop, maybe it's a tablet. That is not true. In fact, a digital computer is anything that meets these three criteria. It has to have memory. It has to have input and output. That's what I/O means on point 2. And it has to have a processing unit. It has to have some kind of brain. So think about if you were just adding simple 2-digit numbers, 17 plus 15. When you add them on a place-by-place basis, when you originally add that 7 and 5, in order to make that computation, you have to recognize that that result is 12. The 2 goes in the ones place, and you have to carry the 1 into the tens place. So that's what it really means when we talk about memory behind a computer. As we'll see here in a minute, originally in computer nomenclature, it was referred to as scratch memory. And you think about kind of making notes in scratch paper. You're making computations, they're intermediate results that you store in order to get to the final answer that you need. So that's what it means by memory, not like a USB stick or ROM where you're plugging something in and you're writing it long term, but rather short-term storage that you're using in order to make a computation. Input and output, that's pretty intuitive. How is it going to be useful if you can't get information in or you can't take it out? So I/O looks a lot different whether you're working on a laptop or a desktop with a keyboard, a mouse, and a screen and speakers than maybe your phone looks, or maybe some modern piece of computing hardware like a head-mounted device in an Oculus Quest or something. In addition, of course, the processing unit, that's just the brains of the computer that actually allows it to do the work. So key ideas, just to refresh on this slide, computers store information in a really simple form, a bunch of ones and zeros, and they can only do a certain very simplistic set of instructions. However, because they have lots of storage, because as we'll see here in a minute, the density of integration on modern computers by Moore's law is very dense. You can fit a lot in a small area. And in addition, because it can do those instructions really, really quick and they can be programmed to do anything, it seems like computers are really these amazing devices. And they are, don't get me wrong, but under the hood, they're pretty simple in their architecture. In addition, note that just because we call something a computer, by what is known, that bullet point there of the 3 criteria is the von Neumann architecture. So that's, you might hear that beforehand. You also hear that computers that have that sort of von Neumann architecture are Turing complete. And we'll talk about what that means here in a minute. But just calling something a computer doesn't mean laptop, desktop. It doesn't mean tablet. It doesn't mean phone. It means anything that has the 3 criteria of memory, input, output, and processor. So let's talk about binary encoding. So take a minute and look at that t-shirt and imagine you saw someone walking down the street with that shirt on. It looks like it says there are 10 types of people in the world, those who understand binary and those that don't. So when you read that last bit of description, it kind of implies that there's really only 2 types of people in the world. So the joke of this shirt is that the number 10 in binary actually represents 2. And we'll talk about what that means after we read through this slide. So we're not going to do a full kind of conversation of how you encode information in binary. It can get really complicated, how you deal with negative numbers, how you deal with fractional or floating point numbers. For those of you that are going down the electrical or computer engineering route, you're going to have an entire course on this. However, for now, the key thing that I want you to realize is the way that you can convert unsigned, which just means positive non-fractional numbers that are in binary to decimal, is the same way that you interpret basic base 10 numbers. So look at this example that I'm giving you here, 727. How do you actually interpret that in base 10? Well, you say the 7 is in the hundreds place, so you weight the digit of 7 by 100, and that weighting is done through multiplication. You're going to take the contribution of the 7 in the hundreds place, you're going to add to it the contribution of the 2 digit, which is in the tens place. So you weight that by 10 or multiply by 10. And the 7 is in the ones place, of course. So you'll multiply the 7 by 1. So you interpret that number as the sum of those 3 contributions. Well, think about a different way you could write that. How could you write 100, 10, and 1? What do they all have in common? Well, they're all 10 raised to some power. 100 is 10 squared. 10 is 10 to the first, and 1, of course, is 10 to the 0. So you kind of see a pattern there. All the digits are 10 possibilities between 0 and 9, and all the place values are 10 to the power, starting with 10 to the 0 all the way to the right, and then the power increasing by 1 as you move to the left. So that same ideal can be used to convert binary numbers to decimal. So look at this binary number, 110. How do I know it's binary? Well, first and foremost, I know it can be binary because it only has 2 digits, ones and zeros. There's no other digits other than ones or zeros, so it could be a binary number. However, it could just be 110. How do I know it's binary? That is what that subscript 2 is in there for. It's to tell me that, hey, this isn't a decimal number, this is a binary number. But how do I interpret it? How do I decompose it? Well, what I'm going to do is I'm going to take each digit, just like I did in the base 10 case, the 0, the 1, and the 1. There's my 0, there's my 1, there's my 1. And I'm going to multiply by the place value. And the place value is assigned depending upon where this is at relative to the start of the number all the way to the right. So that first place here, the digit all the way to the right, the 0, what will it be worth? Well, since we're in base 2, it will no longer be worth 10 to the 0 like it was in base 10, but rather 2 to the 0. In a similar fashion, as we move one digit left, that will be worth 2 to the first. One digit to the left of that will be worth 2 to the second. Now, what's an easier way to say 2 to the second, 2 to the first, 2 to the 0? Well, that's just like the 4's place, the 2's place, and the 1's place. And that's exactly how binary works. The digits go up with multiples of 2. So 1's place, 2's place, 4's place, 8's place, 16's place, and so on. So when you convert those to decimal, if you just combine those together, you'll note this first is worth 4, second is worth 2, this is worth 0 because you have a digit of 0 there. So this is in total worth 6 in decimal. There's some other terms that you want in binary, that you want to know in binary. Namely, every digit in binary is called just a bit. So that's just a word for a single digit in a binary number. If you have 4 binary digits, that collection of bits is known as a nibble. If you have 8 binary digits, that collection of bits is known as a byte. So if that's how computers actually store information in terms of ones and zeros, how do they actually manipulate it? How do you actually have that type of processing or kind of underlying mathematics that's done to do the computation? Or how do you actually implement hardware that actually can store that information in memory? And the key point is that the way that it works is through operations that can be best described by Boolean functions. So I know that sounds confusing, but the key point that I want to get here is in terms of the underlying operations of those ones and zeros. On a hardware level, we can kind of do a bit of abstraction. And what abstraction means is this isn't really the way the hardware is working, but it's a good model that allows us to understand what's going on without digging down to the fact and understanding that really these are semiconductors under the hood. So we could understand them at the semiconductor level. We could understand them at the, as we'll talk about a little bit later, the transistor level. However, we're just going to work on these things that are called logic gates. And logic gates take as inputs binary numbers or binary signals, ones and zeros, and they produce as output binary values as well. And the relationship between the output and input is described by these logical Boolean functions, things like and, or things like or things like nor. And what that actually means is not or exclusive or, and so on. So the key point that I want you to know is that if you have information stored in a digital computer in binary, it is manipulated either for computation or for storage through Boolean algebra type functions, which we're going to represent as logic gates. And in the lab that we'll do next week, we'll get to do a little bit of a gate layout in a software package known as Multisim. Now, these are actually just representing functions, as I mean, but what's going to be special about them? Well, if the input to these functions are purely binary, what that means is that the possible combinations are going to be finite. We're going to be able to count them. So for example, if you have a 2-input AND gate, and either of these two signals, A and B, can take on the value of 0 or 1, there's only going to be 4 different combinations that could be possible inputs to this AND gate. And we're actually going to represent them by counting up in binary, in actual binary numbers. And we'll talk about how to do this more formally. But for now, just realize that the way that you determine the output F, inputs are on the left, outputs are on the right, for a given input value, and the input values can only be 0 or 1 because they're representing binary numbers, is take the particular input combination. For example, when A is 0 and B is 1, the output of the AND gate will be 0. So this truth table kind of tells you how to map from the input to the output. And if you notice, there's a special relationship between the output and the input. You can kind of understand or predict what the output is by just kind of understanding how logic works. So when you talk about an AND gate, notice that the output will be 0, which you can kind of think about if you've seen some of this stuff before as well as false, whenever either one or the other input is 0. Another way to say that that's easier to think about is the only time the output will be 1 is when input A and input B are 1. In contrast, if you look at the OR gate here, notice that its output will be 1 for 3 of the 4 combinations whenever input A or B is 1. So just know that the actual underlying kind of mathematics that manipulates digital information within a computer is based on Boolean algebra, and we can kind of describe the hardware at what is known as the gate level here, and that's the concept of abstraction. So generally speaking, abstraction just means that we're only going to take the complexity that we need in order to understand how the system works, even though under the hood, it's a little bit more complicated. So let's talk about when these ideas actually came about. The one thing that I want you to know is the idea behind the modern computer you're using right now actually was invented or proposed in the early 1800s. Now, they couldn't actually build it then, but people recognized the underlying mathematical feasibility of doing this. And as you see on the right, that is an actual original, that is an implementation of the original digital computing idea by an individual named Charles Babbage. And if you want to read more about him, you can click on this hyperlink. I didn't want to do that. And what you'll find is he's a mathematician by training, but he identified as an engineer. So that's what I mean by computing being by engineers. And what you will find is that this computer, even though it looks nothing like when it was eventually built, the computer that's in front of you right now, it contains elements of the modern computer. It has an arithmetic and a logic unit, the ability to do computation or math. It has the ability to do conditional program control. What that means is to program those basic instructions that it can do. It has a scratch memory. That's kind of the memory that we talked about in the von Neumann architecture of computing. And it has input and output, of course. So this is the first machine that was shown to be Turing complete. That just basically means that it acts like a modern computer and it can be programmed to do anything. You can click on the link if you want to learn more about Alan Turing, a very cool story. Maybe you've seen the movie of Code Crackers historically. Cool guy. In addition, Ada Lovelace is the first person to ever develop a program that actually ran on this Babbage machine that was used to compute Bernoulli numbers. Now, Ada Lovelace, you might have heard that NVIDIA, the company that makes the graphical processing units, actually has a new line of hardware named after Ada Lovelace. So if you've heard of the Lovelace GPU, that's where that actually comes from. So one of the real innovators in computer programming, actually female, which is wonderful. I mean, it's easy to think that historically the people that have made the contributions are only men or they're only white men or something, but there are not enough. But there are lots of cool stories about individuals from different backgrounds that have made really, really key contributions to science. And, wonderfully today, as the opportunities become more and more available, we have more and more individuals really making diverse contributions to the field, which is wonderful. So do click on both of these. They both have very interesting backgrounds if you'd like to read more about it, along with Babbage as well, of course. So the original Babbage machine actually wasn't built until 1941. And unfortunately, if you know what's going on in history then, it was destroyed 2 years later in the World War. But however, in the 2 years that it was used, it was actually used to solve problems in computational fluid dynamics. And if you think about what's going on there in the World War, understanding how planes works and how to design planes, which is a fluid dynamics problem, was the actual application. So again, by engineers through Babbage and for engineers in problems that are traditionally considered mechanical engineering problems. So hopefully you know that these ideas that kind of underline how your computer works today are very old. It's just that we've become better from a kind of manufacturing point of view at semiconductor manufacturing, which is what we're going to look at here. So when you think about kind of moving on from the original Babbage machine to what we would now call a really functional digital computer, they used to be very, very big, as you see on this room on the right. So what was happening is, from an abstraction point of view, the logic wasn't being done in these integrated circuits that are really small. It was being done in vacuum tubes, and you had relays as well. So just things took a lot of space because things weren't integrated. So how's that ever going to be feasible for personal use? You don't have the room, you don't have the money to buy it. And there's an interesting quote in a 1949 article about that actual computer that says the brain, which is a computer, may one day come down to the level of the common people and help with their income tax and bookkeeping. But this is speculation, and there's no sign of it so far. 1949, that's not that long ago. I know on some hand you're like, well, that's 74 years ago, but really, from a lifetime perspective, it's hard to believe that computers used to be that big and people thought they would only be used for income tax. What if they knew about TikTok or whatever we use them for today? So what has really kind of driven the decrease in form factor from this room size to whatever computer you're watching this video on? Well, the key point of hardware that you need to be aware of is this idea of a transistor. And here's the schematic symbol. Schematic just means it's a drawing that represents the connectivity. It's not how it actually looks. However, Don't worry about how it works for now. Just know that it is a digital controlled switch. Basically, by kind of switching the voltage level, which is present on the gate, you can open and close the connection between the source and the drain. So that digital switch is how a modern computer works. A modern transistor works, which enables all of the computing devices. So look at this timeline. Transistor invented in 1947. It actually becomes an integrated circuit in 1960. And from there, the proliferation of computing devices in our everyday life just takes off. When I was born in 1983, there were 5 million worldwide PC sales. In 2021, 340 million, and realize that the majority of the actual computers that meet that von Neumann architecture aren't PCs. So what is making all this happen? You've probably heard of the idea of Moore's Law. And Moore's Law just says that the integration density of transistors on an integrated circuit doubles every 2 years. That's what allows things to become smaller, cheaper, and quicker. And there's some debates of whether we're kind of nearing the end of Moore's Law. It looks like a line when it's plotted, but note that this y-axis is in kind of logarithmic scale. So it is more of a exponential curve, as you would expect, if it is drawn in a linear scale. So summary of module 1 from this lecture, just note that computing is nothing more about the process, the hardware of doing math. The ideas are old. The reason that we have the modern machines looking the way that we do is really advancements in semiconductor manufacturing. Note that those computers, they process discrete information stored in binary, a bunch of ones and zeros, and that they only really know how to do a simplistic amount of things, the instruction set architecture of your processor. However, it is programmable to do really anything you want, including watching this video. So let's look at some example problems here. If we were asked to convert this binary number, how do we know it's binary? Subscript 2. How do we know there's no typos? Well, it's all just a bunch of ones. It can be ones or zeros. How do we convert that to binary? Well, remember, this is the ones place, twos place, fours place. So we have a fours place, a twos place, and a ones place. And if you add those up together, and that's just showing the work here, 4 plus 2 plus 1 is 7. So that's the long way to write it, but hopefully you see how that works. So specify the output of the following logic gate when A equals 1 and B equals 0. We're going to go into this more later. I'm going to give you a cheat sheet, but what you want to do is recognize that this is an OR gate. So if one input is 1 and the second input is 0, remember that an OR gate will produce a 1 as output whenever either of the two inputs, one or the other of the two inputs is 1. So 1 or 0 will be 1. So that's how I'm actually getting that. We'll do a bunch more examples on that in the coming videos, but just wanted to make you aware of it for now. So that is all for the first module of this lecture, and I'll see you all in the next one.